here's the second part of direct variation. This is where we look at some real life examples. Okay, here's a fact. The braking distance, we'll call it D, that a car travels before coming to a stop is directly proportional to the square of its speed. Alright, so what that says is that the distance the car is going to travel, we'll call it D, is directly proportional. So we're going to have a constant of variation, and it's directly proportional to the speed the car is traveling squared. Now, this right here, the K, is going to be kind of important, and it is going to depend upon a couple of things. First of all, the make of the car, the condition of the brakes, and also the condition of the road upon which it is traveling. Okay? So we have to determine K before we can actually use this to predict things. Christina has a white Prius, the fuel-efficient little girl that she is. It can stop in 25 feet when it is going 20 miles per hour. That right there, if we know the D and we know the S, we can solve for the K. Now, once we know what K is, then we can plug different speeds in to the equation and determine stopping distances. So, we want to figure out what the K is and then answer this question. How far will it take to stop if she's going 60 miles per hour? Alright, let's plug in the information we know. It's going to take her 25 feet to stop her vehicle if she's traveling 20 miles per hour. So plugging that into our direct variation equation looks like this. Alright, now before we can solve this for K, we're going to have to do this squaring here. So when we do that, we'll get 25 feet is equal to our constant of variation times 20 miles per hour squared would be 400 miles per hour squared. Alright, now to solve for K, all we got to do is divide by 400 miles per hour squared. So, let's see here. Doing that division, okay, we're going to get 25 feet, fifth of T, feet divided by 400 miles per hour squared. So that's going to be equal to K. Now this will reduce to, there's 4 25s and 100, so this will reduce to 1/16, and the units are feet over miles per hour squared. I left the units on so that you could see how this works in the problem for the 60 miles per hour question. Alright, now that we know what K is, we can plug that in and plug a speed of 60 miles per hour in and get our distance. Okay, so let's do that. Alright, we want to know what's the distance going to be if she's going 60 miles per hour. So let's put our constant of variation in, 1/16 feet per miles per hour squared. Okay, now we're going to multiply that times, she's going 60 miles per hour, so 60 miles per hour squared. Alright, so D is going to be equal to 1/16 feet miles per hour squared times 3,600 miles per hour squared. Well, look at that. Miles per hour squared and miles per hour squared, the units will divide to 1 and we'll be left with just feet. Okay, good. So let's see here. So 1 times 3,600 is 3,600, and then we're going to get 3,600 over 16, and we'll do that division, and it's going to come out real nicely to 225 feet. So it'll take 225 feet, there's 300 feet in a football field, about 3/4 of a football field to stop at 60 miles per hour. Example 2. Now, it turns out that you can use direct variation to make predictions, like we saw in the preceding example. Now, basically, you just need to follow 4 steps. First thing you have to do is write the direct variation equation. So let's take a look at this example and follow down through these 4 steps. Okay, suppose z varies directly as the 4th power of w. Okay. Well, let's see here. The 4th power of w. Z varies directly. Okay. So z is going to be equal to some constant of variation times the 4th power of w. All right, so there's step 1. We've got the direct variation equation written out. Step 2 is we need to find this k. All right, to find the k, we have to be given a little bit of information about the variation, and we have a little bit of information here. If z's 80, we're going to get a value of 2 for w. So if z's 80 when w is 2, find z when w is 3. Well, all right, we know the 80 and the 2, so we can solve for the k. Let's go ahead and do that. Z is 80, and that's going to be equal to our constant of variation times 2 to the 4th power, okay, which is 16. So 80 is equal to 16 times k. Force of habit, I always put the numerical coefficient in the front. Okay, now we're going to divide through by 16. So 80 divided by 16 is equal to k, and 16 will go into 80 exactly 5 times. So our k is equal to 5. So step 2 is done. All right, now that we know what k is, all we have to do is rewrite the direct variation equation with the k in there. All right, so let's do that. So z is going to be equal to 5 times w to the 4th power. All right, now they've told us that w, they want to change w to a 3, so we're going to do step 4. We're going to substitute in that value for w, and we'll solve for the new z. Okay, so we'll put a 3 in there times 3 to the 4th power, which is 81. So z is going to be equal to 5 times 81, and therefore z is, let's see here, oh, I wrote 84, excuse me, that's 81. So that's 405.